Welcome back. Now, in this section, what I will do is take you through a quick proof of Metropolis Monte Carlo method, so that you understand what is the basic probability framework for that, and what is some of the interpretations of that we look for. And then we are going to change our gears a little bit and go back to interatomic potentials, because now that you know molecular dynamics and Monte Carlo methods, what it comes down to is interatomic functions that you are going to use either for molecular dynamics, solving the Newton's equation of motion and trajectory calculation, or you can use MC, Monte Carlo Metropolis method, in order to find the equilibrium configurations. So, let us start with Monte Carlo. And in Monte Carlo, as we said, is that there are, let us say there are two systems and we are going from system R to system S. What kind of probabilities that we look at, which are what we call as transitional probabilities. So, let me first get your document camera up so that you can see what I am writing there. Okay, that looks fine. Okay. So, as I said earlier that we are going to go with the two system solution. So, in this case, let us say these systems are two configuration of the atoms. So, let us draw these snapshots. So, let us say these are 4 atoms here. After a certain time they move to another location slightly, and this is R and this is S. So, these are two snapshots with 4 atoms. So, if you look at the transitional probability we want to find from R state to S, and this is where we can define, let us say V R is the probability of system in state R, and if you look at this V S is system in state S with probability V S. So, with this understanding, now we can look at transitional probability. So, if you look at if P R to S is transition from R state to S, and P S R is transition from S to R. So, if you look at transition probability for V R to go to S. So, let us look at R going to S, it becomes V R multiplied by P R S. So, we get that. So, let us call this as our first slide, and then we go to the next one. So, in this case, now what happens to the system which is R. So, we are going from R to S, now from S back to R. So, this is V S to V R. So, in this case we are going from S back to R. So, in this case what we see is that that become V S multiplied by P S R, and now we use the Boltzmann factor between the two states of potential energy U R minus U S. And so, this is potential energy for state R. So, if you look at this by if we look at equilibrium, then what we need to have is that both transitional probability from R to S and S to R have to be equal. So, now we can look at V R P R to S is equal to V S P s to r multiplied by Boltzmann function minus U s. So, this is the equality that we are looking for in this transition. So, for this transition what we are now looking at, that P r s will be equal to P s r. So, by the virtue of microscopic reversibility, what we see here is that V r over V s will equal to e to the power minus beta U r, which is the potential energy, over e to the factor which is beta U r, and we know beta is equal to 1 over k b t. And so, what this tells us that the V r transitional, the probability is proportional to e to the power minus beta U r. And this is the proportionality which we need to establish in order for us to say that the Boltzmann distribution or distribution factor is providing us the probabilities that represents canonical ensemble with T constant. So, this is where V r is proportional to e to the power minus beta U r, and U r is potential energy and r is position. So, this is the complete, this is essentially completes the proof that our statistics in case of Metropolis algorithm, where we are only choosing some of the ideas and some of the samples which are coming out of the Boltzmann distribution, that we are able to understand the Metropolis is essentially now coming back to the same canonical ensemble, because the probabilities of each particles are essentially coming back with the right kind of understanding from the Boltzmann distribution function. And as you know, in Boltzmann distribution function, especially in when we have T V n ensemble, which is canonical ensemble, the temperature represents the and also the kinetic energy in each particle represent the Boltzmann distribution function. So, this is where we connect Metropolis model, where the selection which is made in terms of the moves, those are accepted, have to belong to certain distribution of the Boltzmann type that allows us to use Monte Carlo simulation with Metropolis algorithm to equate the both situations. It is a very simple probabilistic idea of the transition probabilities, and this is where we are looking into the kinetics also can be calculated by using the master equation of thermodynamics, where now we are able to use this fact of Boltzmann distribution and using the partition function, as you remember from the statistical mechanics, we can solve other thermodynamic situations as well. So, let me stop here, and now we are going to begin our discussions about interatomic potential functions. Thank you.